So thank you very much for having me here. I would like to thank the committee for also reading and selecting my thesis. It's a really big honor for me. So I would first give some kind of high-level overview of the main questions and contributions of the thesis, and then go into some more details. So when I started working on my research, the state-of-the-art in multi-agent planning was distributed heuristic search, which uses heuristic which was computed only locally. So each agent computed the heuristic only using the information which was available to this agent, and they did not communicate about the heuristic. So the first question was if it is possible and how to effectively compute a hopefully good distributed heuristic. And this actually resulted in a number of results here on ICAPS. And I will talk a little bit about the last one, which is the potential heuristic, as Florian was talking about. When I was working on the relaxations especially, it actually turned out that in some cases the distributed heuristic helped, the additional information, but in some cases the local heuristic was actually better. And it depended on a number of factors. But then the question was if we can actually combine those two heuristics in some kind of multi-heuristic search to get the best of both. And that was our planner, which was published last year. And I will not talk about it today. And the third thing I was kind of considering in the thesis was privacy. Because as we were working on the multi-agent planning, it turned out that privacy is one of the most critical or most important concepts in multi-agent planning, but it was not very much studied before. So the question was how to treat privacy in multi-agent planning properly and formally. And so far we have two results. One is kind of general bound on possibilities of privacy-preserving planning, and one is quantification of the information which actually leaks throughout the planning. And I will talk about both of this, hopefully. So now just a very brief introduction to multi-agent planning. So we assume deterministic actions and environment, so it's deterministic planning. We assume cooperative agents which have common goals. And they are honest but curious, which means that they do not alter the algorithm or the communication protocol, but they might try to infer some information the other agents don't want them to know, which is the private information. The planning is offline, is domain independent as in classical planning. So just a very small example, which is quite big on the screen actually. So we have this logistics, and we have two agents. Each agent has their own set of variables and their set of actions. And you may notice that one of the variables is actually the same for both agents. So this is kind of shared variable, which we call public. So this is kind of the public thing the agents can interact on. And then they have some private kind of internal variables, and they have public actions, and those are the actions which use in precondition or in effect the public variable. And then there are private actions, which are again private to the agents. Now actually the kind of transition system of the agent or the public action might look like something like this, where there are the black parts are private and the red parts are public. So the actual kind of public interface of the agent is only something we call a public projection, which is the remaining red part and the red variable in this section. Okay, so now to the actual contributions. So as Florian described the potential heuristic, it actually turns out that it's not only a good heuristic for classical planning, but it's also a great heuristic for multi-agent planning, because if you use the features of the state only, the variables and their values in the state, then we have kind of noticed that you can separate the potentials as well as the variables are separated to public part and private part of the agent, and then you can compute the global heuristic estimate as a public part plus the private parts of the different agents. And we call this agent additive property of a heuristic. And also it has some property which we call agent agnostic, and it means that if the agent uses some action, then this, for example in the search, then this action only can alter the public part of the heuristic and the private part of the owner of the action, but it can never modify the heuristic value of the private parts of other agents. And this can actually be used in the multi-agent search quite well, because now what we need to communicate is only the heuristic for the initial state, which is at the top, and then when the agent searches throughout the search space, it can simply sum all the heuristic parts and obtain the global estimate of the heuristic, like the global heuristic for the complete problem. And then when the state is sent to the other agent, it is sent together with the heuristic values, and it can continue like this. So there's basically no additional computation and communication with respect to the distributed heuristic. Also, the heuristic can be made quite privacy preserving, which means that we can use for the linear program computation, we can use some existing techniques for privacy preserving LP computation, but still some information leaks from the heuristic, for example, the heuristic values themselves, the public potentials and things like that. So now the question is, can we have actually a multi-agent planning which does not leak any private information, which preserves complete privacy? And if so, at what cost? And we have partly answered this last year. We have focused on three properties. One property is completeness, as usual. One property is strong privacy preserving, which means that there is no information leakage. And one property is efficiency, which means that in this case it means that the agents do not have to explore the complete local search spaces. And what we have found out is that we were able to come up with three variants of the PSM planner, which was a winner of the distributed competition multi-agent planning. So we have come up with three variants that each of the variants satisfies two of the properties, but we have shown that it is not possible for such a planner to satisfy all three of them. Moreover, this is not possible also for search-based algorithms, which was shown before, this kind of algorithm. So, and even moreover, we have found out that and shown that in order to be strong privacy preserving, the planner has to be kind of single atomic secure operation. We can take some ideas from secure computation, but they have their own problems, like being exponential in the input and things like that. So if no practical planner is strong privacy preserving, how can we tell which one is better? Well, we can measure the amount of information that leaks throughout the computation. And how to do it? Well, the general idea is that the adversary agent, adversary in this sense means that it is still cooperative in the planning, but it's trying to infer the private information, is actually trying to guess the transition system from the public projection. It's trying to guess what is the actual transition system of the agent. So there are like multiple possibilities, and it's trying to guess which one it is. So it takes some public input, which is the public projection of the problem, and also the solution, which is also kind of public. And it also takes some public output of the algorithm, which basically means the messages which are exchanged between the agents throughout the planning. Now we can take some work from information theory, where they have kind of formulated this equation that the information leak can be measured as the difference between the uncertainty, taking into account only the kind of inputs, and the remaining uncertainty, taking into account also the outputs of the algorithm. So in the case of planning, we basically need to compute the number of possible transition systems based on the input information, so the public projection and the solution, and the number of transition systems possible based also on the exchange messages. Using some information theoretic magic, we can come up with some kind of numbers that can be computed, and this is the actual leakage of the information. And also what is important is that the actions in this particular case are independent, so we can multiply the kind of leakages for all the individual actions. Now on the example, This is the transition system of the ship agent. So it has the public variable and the private variable. And this is the projection only to the public variable. Now the question is, how many transition systems are represented by the single public transition? So we need to take some assumptions. So if we assume that there is one private variable which is binary, so it's the location of the ship, then those are kind of the transitions which are possible. Not all subsets are possible. So for example, if the action is applicable in both variants or both values of the variable and do not change the value, then this transition system is the case. If it is applicable in one value and changes it to the other value, then we have this transition system. And altogether, for a strips action, we have 7 possibilities. And if there is 8 actions, we can compute 7 to the power of 8 and obtain the number of transition system, and then if we take the logarithm, we obtain the information measure. Now what happens when, for example, the agent learns that throughout the search, the action is never applied on one of the states? This means that if it cannot be applied on the state, it reduces the possibilities of the transition systems for this action only to 2, and this of course decreases all the possible combinations for the transition system. And this way, the more information the agent learns, the lower the number of possible transition systems is, and the higher is the information leakage. So just to finish with some kind of view of future work which can be based on the thesis and which we are still hoping to do sooner or later. In the case of distributed heuristics, we would really like to have some kind of general scheme for heuristic distribution which would be additive in the sense that you can add the parts of the different agents. We are hoping to use cost partition for that, but it's still not done or finished. In the case of privacy, there is still open question if it is possible to implement efficient, strong privacy-preserving planner using some secure computation tools. There is a lot of them. Our kind of conjecture is that it is not possible, but we still need to try it at least. And also the kind of leakage measure which I presented is more kind of theoretical concept so far, so we'd like to implement it and measure it on the benchmarks and existing planners and so on. So that's all. Thank you very much.